The ODTBT channel assignment theorem introduces a direct terminological collision with standard particle physics. It categorizes particles into scalar or spinor channels based on their internal recursive structure, using language that immediately triggers established assumptions. In the standard paradigm, the word spinor specifies a relativistic spin one-half wave function governed by the Dirac equation, or a representation of the Poincare group labeled by Wigner spin. It describes external spacetime symmetry. This table directly compares Wigner spin classifications against ODTBT channel assignments for a corpus of 10 particles, exposing an immediate structural paradox. The electron is a classic spin one-half particle, yet in the ODTBT framework, it satisfies a recursive closure condition and utilizes the single-seed scalar channel. Compare that to the K0 meson. It is classified as a spin-0 pseudoscalar meson, meaning it lacks external spin entirely. However, its internal structure requires two distinguishable recursion scales, placing it firmly in the dual-seed spinor channel. Particle types of the same Wigner spin use different channels, and particles in the same channel possess different Wigner spins. The ODTBT channel assignment operates entirely orthogonal to spacetime symmetry. It is a strictly internal metric. Proving a physics model requires separating archaeological pattern matching, tuning parameters to fit known data after the fact, from true theoretical prospecting, where the math dictates the architecture before the data is processed. The ODTBT framework assigns particle mass ratios to Pythagorean triple Grant means. The mathematical challenge lies in justifying exactly when to use a single optimization parameter and when physical reality demands a shift to a dual-parameter space. This flowchart tracks the three-step derivation that bridges the gap between quantum chromodynamics and recursive geometry. The sequence begins with a strict flavor analysis of the particle's constituent quarks. That physical data informs a mathematical closure derivation, which establishes the necessary recursive scales, culminating in the computational validation. Running this sequence on the K0 meson yielded a predicted spinor channel assignment. Upon computational testing, that precise configuration returned a level 1 error rate of 0.0053%. This sequence did not tune a formula to find the mass. It evaluated the initial physical conditions of the quarks, computed the necessary recursive geometry, and confirmed that the resulting structure naturally yielded the physical mass. To understand why the sequence works, we evaluate the baseline scalar channel requirement derived from the RCAM-HE version 2 framework. Within this framework, specific coupling functions, labeled as JJ, govern the recursive streams. For a particle to exist in the scalar channel, these coupling functions must perfectly vanish. The J coupling vanishes when, and only when, the two recursion streams are entirely indistinguishable. Mathematically, this means the phase strains are equal, delta phi 1 equals delta phi 2, and the recursive closure rates match. This plot models the visual consequence of these equations on the lock potential, designated as lambda n. When the closure conditions are met, the indistinguishable streams produce a single lock potential curve to maximize. This is the scalar channel, utilizing a single seed. The electron operates here. When the coupling functions fail to vanish, the indistinguishability condition breaks. The optimization space experiences a structural bifurcation. The broken closure generates two distinct lock potential curves. Finding the physical mass ratio now requires a joint optimization over both depths, defined by the geometric mean of the two diverging streams. Failing the indistinguishability condition dictates a topological shift in the optimization lock. The particle mathematically requires two seeds to account for its internal asymmetry. The mathematical trigger that breaks this closure condition originates directly from the particle's constituent quark content. The K0 meson is composed of a down quark and an anti-strange quark. The strange quark sits at roughly 95 mega-electron volts. The down quark is only 4.8. This constitutes a severe flavor asymmetry, with a mass divergence ratio nearing 20:1. This extreme mass divergence prevents a single effective recursion scale from forming. The down quark and the anti-strange quark are forced to select entirely distinct recursion scales. Those distinct scales translate mathematically into distinct Grant mean seeds within the recursive structure. Distinct seeds guarantee that delta phi 1 cannot equal delta phi 2. Therefore, off-diagonal flavor asymmetric quark content forces a failure of recursive closure. Before a single numerical evaluation is processed, the physical makeup of the K0 meson dictates a spinor channel assignment. To test this derivation, Task 2C initiated a comprehensive grid scan. It constrained the depths between 2 and 10, evaluating all Grant mean pairs. This chart graphs the level 1 error percentages for the K0 meson, contrasting every forced scalar channel seed against the predicted spinor result. Forcing the single seed scalar channel fails to accurately model the particle, yielding a high 10.23% average error baseline. The predicted dual seed spinor scan, utilizing the geometric mean and discrete quotient mean at depths 3 and 7, dropped the error to 0.0053%. That result constitutes a factor of 1929 improvement over the best scalar baseline. Crucially, this optimization formula is identical to the one previously used to validate the K+ meson. The massive leap in accuracy stems entirely from assigning the correct physical structure, not from tweaking an equation. Continuous optimization algorithms only converge on physically accurate mass ratios when they are rigorously constrained by the correct discrete symmetries, in this case, the channel assignment mandated by the flavor asymmetry. The channel assignment theorem must also hold for boundary states. The eta prime meson serves as a primary test case due to its formally flavor-symmetric composition of up, down, and strange quark pairs. Because its quark pairs are diagonal, the framework correctly predicted a scalar channel. However, its computed zero divergence vector proximity, the z-value, landed at an anomalously low 0.247, placing it deep into edge territory compared to the standard corpus. These plots visualize how the Feldman-Kroll-Steck framework resolves this proximity anomaly through U1A anomaly-driven mixing. Look at the flavor-content coupling. The physical eta prime meson couples predominantly to strange quarks at a ratio of roughly 9:1 against light quarks. It is not a pure flavor singlet. This internal mixing introduces anomaly-driven complexity, physically pulling the optimization seed away from the clean, discrete vertices where the z-value approaches 1. The lower the flavor purity of the basis state, the lower the resulting z proximity value. The math maps the physical reality of the anomaly. Even when a particle correctly utilizes a single seed scalar channel, the exact numerical value of its geometric proximity metric scales precisely with the quantum purity of its underlying quark state. A theoretical framework is only as robust as its testable predictions. The channel assignment theorem provides an immediate roadmap for undiscovered parameters. Moving into the heavy quark sector, we examine the untested D and B mesons. Every particle on this list is an off-diagonal, flavor asymmetric meson. Consequently, every single one is mathematically locked into a predicted spinor channel assignment. This establishes a strict falsification criterion. If any of these off-diagonal heavy mesons achieves a sub-1% error rate utilizing a single seed scalar channel, the flavor asymmetry derivation is broken and the mechanism is proven false. The closure condition successfully bridges standard QCD flavor structure and Pythagorean recursive constants. It removes the guesswork from channel assignment. The high accuracy mass ratios observed in the ODTBT framework are not artifacts of data fitting. The recursive geometry is mathematically demanded by the fundamental constituents of the particles themselves.